Today I would like to show how you can create a shape like this. This plant is called Romanesco Broccoli, which has some significant features. As you can see, if you look at this shape, it's basically a fractal based shape, and in this website it explains what kind of fractal or algorithm could be used to make this kind of shape, and it says that it is based on a Fibonacci fractal. So we'll like to use that to make this shape. So I searched for this Fibonacci spiral, how to make these things, and there is a website in here explaining some mathematical equations, how you can create a list of points which creates a Fibonacci spiral. So I would like to use that in order to create one, and based on that spiral I will try to make this kind of shape from scratch. Okay, let's start. First of all, let's make a geometry, and let's first create a list of points which represents a Fibonacci spiral. So okay, I'll start from point, angle, and change it to detail so that I can make a point from scratch. And let's see, first of all, let's make a parameter called num, stands for number of points. Okay, let's also create a null parameter, null geometry, null node. Name this controller to gather all the parameters that I'm gonna use. Okay, and I'll create a integer num, and the range could be like 0 to 100, for example. Let's link this to the wrangles parameter here. Okay, now let's create some points. Okay, for int. Now first thing, I think I need to refer to the website which have equations to create a spiral. So let's look at it, and let's say it says the spiral exhibit in nature can be modeled by a simple spiral of points generated and polar coordinates by starting at r equals 0, a equals 0, and then repeated increment. Okay, so basically I need to have this one as an angle which increments by this angles, and this phi is this one, and the r is the radius which increment by 1. Okay, so let's make that in Houdini. Okay, so first of all, let's give a phi which is 1 plus square root 5 divided by 2. Okay, and also the angle, step angle, is 2 times pi times phi minus 1 divided by phi. Okay, then I'm gonna make a new point, add point, And before setting the position, I'm gonna make a vector position set. Okay, and since it was explained in the polar coordinates, I'm gonna use cosine and sine to set the angles, set the positions. Now, first of all, I think I need to set the radius as well, so let's set the radius. Let's say, I'm gonna say radius equal, well, this I increments by 1 itself, so let's do that. And then this is position, so let's use cosine. And I'm not sure about the height yet, so let's leave that for now. Sine for z. Okay, and I'm gonna use the angle times I, so that the angle inside cosine and sine will increment it by angle, which I set it here. Okay, and times I. Right, and also I need to multiply this by radius. Okay. Finally, put this inside a position. The geometry input is 0. Right, let's see if I got anything. Yeah, I think I got some points here. Let's increase the points to like 100. I'm not sure if I'm seeing it as a spiral. Let's increase that a little bit more. Now it starts to show some spiral shapes. Yes. So basically I think it's correct. Yeah, looking good. Now I don't want to make it too much of a point because I'm gonna make it as a geometry and using fractal repetitive recursive functions, so it's gonna be tons of points afterwards. So I'm gonna go with 100 for now. Okay, now that I have a point, let's try to move this on upward to the y direction. I can change it here, I guess. I think I want to move to the negative way, so I'm gonna type minus I for now. And I guess I would like to make a new parameter here to control the height. Ratio. Okay, and multiply here with that height ratio. Okay. Now let's add the parameter here as well. Maximum to 2. Let's link this. Okay, let's keep it 1.25. Okay. Also, right now it's a bit too straight up cone-like shape like this, so it doesn't look that natural. So I wanna make this shape a little bit like this, more skewed. So I think I need to change this radius. So let me see. I think I can create a equation using a power, and let's say I also need a new parameter. Maybe I'll just say a radius ratio, and let's divide this by a maximum of numbers. So since I'm gonna divide I, this number will gonna be maximum in the for loop. Okay, so let's go back and create a radius ratio. And let's go up and create another parameter here. Radius ratio, radius could be from 0 to 1. Okay, copy this and paste it here. Right. And okay, I think I also need to multiply this by I, since this is just a ratio for each I step. Okay, looks good. So this one is controlling how far this cone become pointy. Okay, good. Okay, let's go with this size for now. Okay, what else? I think I can go with this for now. Well, I guess the next thing I would like to do is to create a surface from these points in order to get the normal direction for each point on top of this cone-like shape. But right now it's just a collection of points. You cannot get any normal directions from it, so I gotta make a surface. And in order to make a surface, I think what I can do is to extract some points as a line with the point collection of point that makes a spiral curve. So let's find that from these points. And what I can do to test out, what I can do to find out the connections, I think I can make some conditions here. If I remains of, let's say, like 3 equals to 0, then let's make a new array here. Push that point inside the array, and after that make a new line based on those points and see if it connects, if it have a nice spiral curve in order to use it for lofting to make a surface. So line, spiral, add prim. It's gonna be polyline and PTS. Okay. Now, okay, it does make spiral curve, but it's a bit too drastic. So let's increase this number a little bit, like to 5. Yeah, 5 is okay, I guess. But still a bit too drastic. Oh, this is not good. 7, no. 8. Yeah, 8 is good. Okay, let's remember this number. 8, 9, no. 10, no. 11, no. 12, no. 13. Oh yeah, 13 looks pretty nice. I mean, the spiral curve is a bit not that obvious, but I think with these curve, I think it's much easier to create a loft shape to make it a cone-like shape. So let's use this number 13 as a step number to extract those spiral lines. So what I want to do is to go up here and make a new variable equal step and make it 13, and for each numbers in steps, make a loop and add the point to this 0, 0, 0 position, because I always want this spiral to start from this 0, 0, 0 so that I can make a non-opened loft surface. Okay, so gonna have to make 0 set 0, 0, 0. Now right now the point's position is duplicated, so I'm gonna use a fuse afterwards to merge it all together. Right, and let's set the attribute for each point. Let's name this connect, and with the value I, so that the points that have same attributes called connect will be connected as a spiral curve. Okay, now here comes here after I make a new point here for these points, need to also set the point attribute to the point with the I and remains of step, which is 13. Since I is going to be greater than 13, I have to divide it by step to get the remains. Okay, now let's see. And let's remove this. Now let's go to the geometry spreadsheet. And yeah, I have those connect, so let's use that to actually create a line. So bring up a add node, go to polygon by group and by attribute and connect. And I don't seem to see anything here. Am I missing something? Let's go back here, connect. Okay, I typed on the group. I have to type it on the attribute name. Okay, So now I got the spiral curve here. Let's see if I change this 13 to something like 8. Still gives you the spiral curve. I mean, either way is fine, I think, since what I just wanted to do is to make a loft shape from it. So connect a poly loft to here, and now I have a problem lofting it, obviously, and the reason is because if I look at the curve and the curve order, the order is pretty much random, so that is why the loft doesn't make a clear surface, the cone-like surface. Well, this itself is good. I mean, looks good, but it's not my purpose. So let's change the order of this primitive first to make it able to get a correct surface. Okay. Now, before doing the loft, let's fuse the points here. Okay, and in order to sort out those primitives, I can use this sort, but for primitive sort, there's not much thing that I can use to sort out this circle arrayed objects. So I'm gonna use an expression, the attribute, and give it an attribute to each primitive, like in which position inside the circle is positioned. Maybe I can just set the angle from the 0, 0, 0 positions for each my endpoint of these primitive, so that I can obviously set the orders based on those angles. So let's give a primitive wrangle. Oops. Right. And let's write some code here. Okay, first of all, I want to get the point correction point list from those each primitive. So I'm gonna use a prim points at prim num. Okay, and just want to get the last points. So it should be stored in the last position of this PT points, because the points being made from top to bottom. So int last pt equals to pts len pts -1. Okay, this will be the last point's number, index number. Then let's get the position of that point. Okay, and let's set the position of that point, the y value to be 0, because I don't need that value in order to calculate the angles. Okay, and let's also normalize this vector. And let's check out if I get the correct point by adding this point inside the 3D view. Okay, so if I close up, okay, I think I don't see it. Oh yeah, I have to enable this one. Yeah, those here, those are the points which are normalized from these points, the endpoints of each primitive. So let's use that point to calculate the angle. Okay, so calculating the angle based on the 000 position is pretty simple. I'm just gonna use the A10 function with the position Z and position X, which will give you the radians angles. So after that, let's feed the attribute angle with this value angle. Okay. Now let's go back to the geometry spreadsheet, to the primitive, and yes, I have those angles. Now let's use that to sort out the primitive. On the by attribute for the primitive set, let's set the attribute angle. Now let's look back to the number of primitives, and I can see that now it's ordered correctly. 0, 1, 2, 3, 4, 5, 6, 7, 12. Good. Alright, then let's go back to the loft end. It's clearly making a clear surface, and I want to close this thing, so VWrap to on. Okay. Let's hide those. Now, thing is that right now it's not that totally closed, because this here, the bottom part is opened, and since I want to make it 3D printable afterward, as well as being able to render easily, so I'm gonna use the VDB to convert it. So in that case, I need to close this bottom shape to make it a closed shape. So let's try to do that. First of all, let's look at the normal direction of these each points. And do I see any? I think the vector is not that obvious here. Let's go back to the display options, and where is it? Here, I guess. Scale normal. Okay. Now it's going inside, which I don't want, so let's flip that using the reverse node. Okay. It's good. Next thing. So in order to get the bottom part, let's use a group. And make it points. And let's select the include by edges and unshared edges. And disable this base group, and let's name this like bottom. Now the group is only attached to the bottom points, which is a opened edge part. Okay, so let's extract only those using blast. What was the name? Bottom. And just get those. Okay. And let's connect those to create a wrapped circle-like curve using add. Now here comes a similar problem here. The order is pretty much random, so it's not creating a wrapped circle. So I also need to order this point as well. Now let's do that. Okay, so this time I'm gonna use the point wrangle. And the thing that I'm gonna do is pretty much the same for I did to the primitives. Since it's already a point, it's much easier. I'm just gonna feed an angle A10 to C, point C and point X. Okay, and then use the sort to sort out the point by an attribute using the angle. Good. Now let's also close this, and it automatically creates a polygon. One polygon, but I would like to divide this to make it triangulated. Yeah. Or I could also do remesh to make it more smoother and the bottom, but right now I think it's okay with this. I don't want to make it heavy, too much heavy. And this part you don't really see, so it's fine. Okay, now for the original corns, let's attach the normal node to create a normal vector for each point. Yeah, and after this, merge these together. And fuse to weld the points. Okay, now I got the base. What I want to do next is to do some fractal operations to scale this base surface and place it on each point on a surface with using this guide as a normal as a guide, and repeatedly do that to create a fractal shape. In this case, Romanesco Broccoli like shape, like this one. Now, I guess I can do in two ways. One way is to use a for each node, or another way is to use the solver, but solver could be pretty heavy and uncontrollable compared to for loops, so I'm gonna go with the for each loop for this example. Okay. Now let's try the first attaching. Well, what I mean is to attach this shape to each points. So I'm gonna use a what was it? Copy stamp. And before doing that, I'm gonna pack this geometry. This. Okay, and let's try to copy it. Oh, it's a different way. Okay, and what happens is that I guess the orientation for copying is not correct, so I think I need to modify this packed geometry's position or rotations a bit to orient it in a correct direction. Now I have just put a transform here. Now first thing, let's rotate this, and the direction might be okay with these, but I don't really see if it's correct or not, since what I want is that the shapes which is close to the top part should be scaled up pretty small, and the bottom should be scaled up a little bit bigger. So obviously this is not correct in terms of scale. So in order to make that possible, to make the scale bottom larger, the scale on top smaller, we need to set the P scale for each point of this base surface. So let's go back and run here, I guess, to the first one. And let's set the P scale somewhere. Now where can I do that? I guess I can do here, where I'm making a new points. So set point attrib p scale pt, and here I have to set some numbers here. So let's say 1, no, I, yeah, it has to be based on I, and but I don't want to make it too large, so let's divide it by num and see how it goes with this. Now looks a bit better, but still a bit too big. So let's have another parameter here, float scale ratio. And come here and make the same name, scale ratio, the range from 0 to 1, and copy this to here. Now let's multiply this number with the scale ratio. Now it happens to become better, much better. Now the thing is that it's being offset inside this base surface, so I have to move it upward, obviously, because for the final I want to merge this base surface together with this copied needles. So I have to move this needles outside this base surface. So I think what I have to do is to go to the transform to move this geometry to I think for this case Z direction. Yeah. Now how much should I move is the height for each needle is based on this number here. So I'm just gonna copy this parameter and go back to the transform and paste it here. Good. Now it's going above this base surface. Okay. Now the number of needles might be a bit too much to calculate fractals. I'm gonna set it to 80, and still it's fine. Still I think it's fine. Right. Now I do see some spaces around here. I don't want any spaces. I want the packed geometry. Not this pack, but needles without any spaces. So I think I need to modify this one's P scale a little bit more. Okay, let's see what I can do. What I can do, I guess I could add initial numbers like 0.1. Yeah, it's too big. Or 0.01. Not enough. 0.015. Yeah. Or 0.02. Yeah. Looks good. But the top part, not that good. 0.15, okay. Let's go with this 0.015. Maybe I could also parameterize this one as well, but I'm just gonna keep it as it is for now. Okay. And what I need to do now is to set up the fractal operations from here. Okay. Let's set the null first. Let's set first. And this one is the base, so set the null. I'll name it base. Color it. So that later on I want to merge these things too, so I'm just making visibly easy to see. Now, since these are all packed geometries, right now there's like 80 of them, so I'm gonna use a for each loop, for each primitive, connect it here. Okay, in this case, okay, I just saved the file since the operations I'm gonna do next is pretty heavy, so be careful. Now, let's connect the null here. It doesn't mean anything, but it's okay, and I'm gonna unpack so that I can use the points to for the points on the surface with the normals to use the copy stamp again. Okay, and then let's hide these, and let's also set the P scale for the new surfaces, since each surface has different size now. Obviously, if you look at this, see, and which means you have to set a different P scale for each points on each primitives in each surfaces. If you set the same P scale, you're gonna have the same like size cones copied on this each surface, so that you don't want that. So I'm gonna make a point wrangle here, and not this one. Gonna connect with the unpacked one, and before you unpacking, if you look at the point, okay, let's go to the copy stamp here and transfer the attributes, especially the P scale, which in return, if you go to the point attributes for copied packed geometry, you'll see this P scale, and I'm gonna use this as a guide. And here you still have wait a minute, should be having this. Okay, you have this P scale inside here as well, so let's use that as a guide to convert this original P scale on the point position of each surface right now here. Now what I want to do is that let's do like this. Modify the P scale using the original P scale times point to refer to the second input. Okay. And let's see what happens. let's use the copy stamp again. And what I want to copy is the same thing as this one. And the place I'm gonna, I'm gonna copy is this one, and then connect it here. And voila. Yeah, you have now have a first step, first iterations of the fractal. And looks pretty good, I think. I think so. But the next step will gonna be much heavier. Right now it's just what's the number here? Wait. It's just hanged out. Okay, right now I have like 6,400 primitives, packed primitives. But for the next one will be much higher than that. It's like 6,400 times 600 400s. So in order to prevent a unnecessary geometry, to create an unnecessary geometry, like right here, right now, it's already, the geometry is too small, I mean, to recognize. So those kind of geometry, I just can ignore it. So let's create some conditions to ignore the too small geometries inside here, I guess. What I can do is that if P scale is less than some numbers like 0.004, remove the point for the impact geometry. Now this is the first iteration, so it doesn't really make a impact, I think. Well, let's see if it changes any numbers. And yes, some geometries have been deleted and you don't really notice it because it's too small. So that's fine. I think that's good. Now this is the first iterations. I also want to do another steps to make it more like a Romanesco Broccoli fractal shape. What I can do is that I can just copy paste this set for each loop, but that's not smart, obviously. So I'm gonna make a different way to achieve that. Okay, the thing I'm gonna do is to make a for loop, but not the primitive, but using the for each numbers to set how many, to say how many number you want to continue doing this. Now let's bring up here and bring up here. And now first I need to set the settings. Now this is right now fetch input, but I need to set it to fetch feedback, because each time you calculate you want to create a new geometry. Alright, and based on the inputted geometry. Okay, now for these, for the end one by count is okay, merge each iteration is okay. Now I don't want to make it iterations too big. I'm just gonna set it to 2 iterations. So I'm gonna just run this 2 times. That's what I want to do. Okay, now after all, it should be simple. I'm just gonna connect the first one to here and here, and then connect it to here. And let's save this before continue and activate this one. And I think it's not working. Let's see what is going wrong here. Okay. Let's apply this and go back here. Okay. Okay, same number, so it has been only done once. Okay. So it's been set it to fetch feedback. I think it's fine. Yeah. Oops. And for this one, by count, merge iterations. Is it this one? Oops. Oh. No, I don't think it's this one. Let's go. Let's set it back to merge iterations. Okay. Let's see what I have missing. Okay, I think I got why this doesn't work, because I haven't transferred a p-scale for this one. Oops. Okay, now it seems to work. Wow. Yeah. If you look from far away, it looks okay. It's a bit too sparse, I guess. What I can do to correct this is that I can move this a little bit upward for this one. So let's say times 1.1. A little bit better. Well, let's not do that way. Wait. If I do like 1.2. Yeah, a little bit better. Guess this is fine. Yeah. All right. So now that I got this geometry, next thing I want to do is to make it, let's say 3D printable, or make it easy to render. So let's convert these to VDB volume. Now I also wanna, what was this? Okay. And do we have this one here as a base? Nope. So let's first merge. Okay, this one is the fractaled. Now the first thing to merge is this base. Oh, not the measures. Merge. Right. Now first thing, base. Second is this one first, and then finally a fractal. And there you have a collection of geometry all merged up, packed up. I guess due to too many polygons, it's showing like a LOD. The base one. Oh, not this one. I need to use this fused one. Yeah. Okay. Since this is the one that is closed. Okay, let's go back here. Just doing some heavy calculation. Okay, now converting these is pretty easy. I think I can use the PDB from polygon, and let's set the volume size to something like 0.2. Save this before doing this. And wait a little bit. Okay, I think it's been done. Pretty detailed. Now let's convert back to polygon. Convert PDB. And let's set it to polygon, save this, and go for it. Well, that was fast. Now these are all polygon now. Now, at this point, it's pretty much done. I just want to color this a bit to make it look like more like a broccoli. So, to make it more colored with the shade, I think I can use some technique I use a lot, using a dot product to calculate whether the geometry is facing the mesh face is facing upward or downward. Now the way to do is to set the call attribute with the dot, with a normal, and the direction on the y-axis direction, which is upward in this case. Now if you go to the point attribute, you will see the call, which is from -1 to +1. So I can use that to color this shape. Let's go to the ramp from attribute and use the call, which I have just made, and the range is from -1 to 1. Now the downside is, the bottom side of the face will be use this color, and the upside will be use this color. So let's set some colors here. The downside could be black, and I can add another value like dark green here. For here, I think I can add a light green like here, and maybe I can modify this one as well, more like a yellow green. This one as well, more of a yellow. Yeah, becoming more like a, and let's darken the shadow a bit more to make it more 3D looking. Looks good, I think. And give a little bit of contrast with the high valued color. Yeah, but basically that's it. And voila, you can make a Romanesco broccoli like this, and it's all merged together as a one polygon, so you can send it for 3D printing as well. And that is pretty cool, I think. Okay, that's it. Thank you.